Attention score. Attention score is a revolutionary concept in NLP and machine learning. Imagine reading an article. You don't give equal importance to every word, but rather focus on certain words that help you grasp the main idea. Similarly, the attention score mechanism allows models to focus on certain parts of the input data that are more relevant for a given task. For example, in language translation, certain words in English may have multiple meanings in another language. The attention mechanism ensures that the model selects the most contextually appropriate translation. This tool will help you understand how attention works and how it is calculated. Let's explore it. A very simple example of attention score could be from the concept of how a dictionary or hash map works. We typically have some keys, and for each key there can be a value object. For example, here we have a system where the keys are apple, banana, and chair. Their corresponding values are 9, 6, and 3. If we run a query against this system by asking the value when the query is apple, the system returns the value as 9 with a 100% probability. We can change this query to banana and we get the value as 6, which is expected. We can select chair and we get 3. This is all good. Now let's say we ask the system to return a value when the query is fruit. The system is clueless in this case, as no key matches with this query. Even though there are a couple of fruit-related keys, there's no mechanism to match apple and banana to a fruit. So even if our attention is on the word fruit, we cannot infer any meaning of it using this system. To address this problem, we can use the vector forms of all these scalar quantities, the key, the value, and the query, just like we can use composite keys and values in dictionaries and hash maps. Because in NLP, or natural language processing, we already have a concept of representing words as embedded vectors, we can use them to represent the key, value, and query vectors. Then using these vectors, we can define a mechanism to associate the query with key and values using vector dot products and probabilities. We have a couple of such examples, so let's try one of them. Let's select the vector example of fruit and things. The same tokens, words, or entities are used here again: apple, banana, and chair. These entities can be vectorized using the attributes such as sweetness, durability, and texture. To make things even easier, we have used the same attribute values for both key and value. In terms of attribute numbers, apple has more sweetness than banana and chair. Chair is more durable than both apple and banana. And finally, banana is richer in texture as compared with apple and chair. Please note that in a real-life system, these numbers are generated using some training mechanism involving various forms of embeddings. Now, we want to run a query on the system, and this time, the query is not a single word or value, but rather a vector of values in terms of sweetness, durability, and texture, like here. In other words, we are asking to match keys and values where the sweetness is equal to 0.8, durability is equal to 0.2, and texture is equal to 0.1. Let's press the compute button, and here we go. The top match for this query is apple, with a scale dot product score of 0.44 and the softmax value of 0.37. This match can be represented in the value embedding space as a vector with components as sweetness equal to 0.33, durability equal to 0.04, and texture equal to 0.11. The benefit of this system is that any word with similar embeddings will also be resulted in response to the requested query, or attention vector. Let's explore how we calculate the scale dot product, softmax values, and the output values. First, let's see how this column, the scale dot product, is calculated. This is the formula. The scale dot product is the result of taking the dot product between two vectors k and q and then dividing it by the square root of the dimensionality of the vectors. The scale dot product measures the similarity between two vectors k and q while accounting for their dimensionality. By scaling, it prevents large dot product values from causing numerical instability. Next, we can take a look at this column and find how to calculate the softmax. Here's the formula to calculate softmax. Here, xi is the ith element of the vector x, e is the base of the natural log, and the denominator is the sum of the exponential values of all elements in the vector. The softmax function transforms a vector of real numbers into a vector of probabilities. Each probability in the result is in the range 0 to 1, and the sum of the probabilities is equal to 1. Finally, we calculate the output, which is the attention score for each entity. This is the formula. We just do element by element multiplication of the softmax to the value vector v. So basically, we take the softmax of the scale dot product and then multiply it by each of the values in the value vectors v. The attention score quantifies the relevance or importance of certain input data points when producing an output. It measures how much focus a model should place on specific parts of the input, enabling the model to dynamically weigh and prioritize information based on context. This covers how this tool helps us understand how attention works and how it is calculated. Please feel free to play with the tool by choosing various examples and trying different values of the query vector and analyzing the scale dot product, softmax, and the output as attention score.